Alright, welcome back. We are going to continue and talk about the different styles that volcanic eruptions can erupt in. So we'll go into effusive versus explosive first. Those relate to a lot of these others. We'll get into some of the main categories, and then we'll talk about some individual events that will occur during these eruptions. So that's why I have a split here in these two columns. So the lava flows, lava domes, so on and so forth. Those also can be associated with various eruption styles. So these eruption styles are broken up for various reasons, but one of the main reasons is pyroclastic versus effusive, or explosive versus effusive. Pyroclastic, so you can think Mount St. Helens is a good example of a pyroclastic or explosive eruption. And Mount St. Helens, well, it was pretty big, and the overall scale of volcanic eruptions, it really wasn't as big as it could have been. But you can see really big explosion there, lots of ash, lots of gases, a lot amount of destruction with those pyroclastic or explosive eruptions. Effusive eruptions are more calm. These ones are more mafic in composition, so they typically have basalts resulting from these eruptions. So you get more lava flows, calm rivers of lava, maybe a little bit of lava fountains, but not the giant explosion like you would see with the pyroclastic eruptions. So effusive, they're more mafic. They have a low viscosity, a low resistance to flow, whereas pyroclastic eruptions are more explosive. They are more felsic. They have more quartz present, which makes that magma stickier, and have a high viscosity, a high resistance to flow. There's a previous video this week where I talk about viscosity and how it relates to your eruptions and different landforms that we see. So definitely check that out if you're having a hard time with these terms. So with each of these categories, we can break these down even more, and that's where we come into these various styles. So here's a nice little diagram from OSU's Volcano World website, which you're going to visit a lot this week. They have some great examples of these different types of eruptions. So this breaks it down by height of eruption column versus explosiveness. So you can see the Hawaiian there is in the lower left corner. It has a very small eruption column, and it is effusive. It's a calmer eruption. Whereas the other side of things, the ultraplinian, really, really high eruption column and very, very explosive. So we can break it down by explosiveness and also how high that material was shot up into the air. So to have a more realistic diagram here, we're going to go through the majority of these, and you can see just how these compare as far as the Icelandic, Hawaiian eruption, very little eruption column, none in this case, versus the Plinian, which is a huge, huge eruption column. So to get into it, Icelandic, named after where we see these in Iceland. This is an effusive, a calm eruption. Typically we have fissures, so the crust is being pulled apart in Iceland. So we have both the divergent boundary here and a hot spot combining. So we get these huge fissures that can develop in the Earth's surface, providing a pathway for that magma to rise through. Because of that pressure decrease, we have decompression melting, and we get these lava flows that develop. So these are typically basaltic in nature. Here on the bottom here, you can see a little example of what a fissure eruption might look like. The next type, Hawaiian, named after where we see these, Hawaii. Hawaiian eruptions are very similar to the Icelandic. They're also calm, effusive, produce basalts of various types. So we can just have the irregular basalt, we can have porphyritic basalt with olivine crystals in it. We can see some ash, we can see vesicular basalt, we can see scoria. So any of these more mafic type rocks we'll find in these this Hawaiian and also with the Icelandic eruption styles. So the difference between the Hawaiian and the Icelandic is where is the stuff erupting from. Icelandic, there's fissures that open up and we have more of a linear track that the magma comes up through and creates those lava flows, whereas the Hawaiian, we typically have a high point. We have an actual volcano where an event where that material comes out of. And typically these Hawaiian style, they're much, much bigger scale. these shield volcanoes are just absolutely enormous. We're going to talk about these more next week. But these can also have some smaller fissures that can develop on the flanks of the shield shape, and also some other small vents that might pop up along that volcano. Strombolian, so we're getting a little bit more explosive here. So this one might have a little bit of both, maybe some lava flows and also a little small, moderate eruptions of magma and ash that actually can occur regularly on a regular basis. And with these, we see we have a pretty small eruption column, as you see in that diagram. Here's a satellite view of Stromboli, an example of a Strombolian eruption type. And these are typically intermediate in composition. They can be more intermediate to mafic, just depending on where that magma came from, how long did it take it to rise through the crust, how much of that fractional crystallization and melting of the surrounding rock has happened. So those are Strombolian, a little on the small side, but still a little bit explosive. Next step up, Vulcanian. So this is going to be a little bit bigger, taller eruption column. Again, explosive, very similar to the Strombolian. We just see our eruption size much bigger, a bigger eruption column reaching bigger heights and producing much more ash that might impact larger areas around that volcano, whereas with the Strombolian, we had only maybe the localized area right around the flanks of that volcano being impacted by that ash. So we're getting bigger and bigger. The next one is Planinian and caldera type. So these are very similar because they have huge eruption columns that spew this ash way up into the atmosphere. These can produce their own weather patterns. We can see lightning in some cases. Both the Plinian and caldera type can produce these huge columns, but with the case of calderas, we have enough material ejected out of that volcano that whole nice cone shape that we see just completely disappears. And the reason for that is because the magma chamber below empties out completely, and that structure on top doesn't have that support anymore, and so it collapses down into itself. So we end up with similar things like the Yellowstone caldera is a good example, or Crater Lake is another good example. So these extremely large, very explosive, gas-rich, lots of ash that can spread for hundreds and hundreds of thousands of miles. In the case of Yellowstone, we see layers of ash that spread all the way across the United States. And some, if it's shot high enough into the atmosphere, can go around the entire globe. So some of the products that we get with these various eruptions, and some of these we can just have maybe instead of a larger eruption, maybe we just have a lava flow that's produced. So the lava flows are typically going to be effusive. We see that nice flow that happens just like a river would flow. So we get what's called pohoihoi and a'a. So pohoihoi is that nice ropey look that we see. A'a is towards the end of that flow where it's much cooler and it gets more blocky and pokey. And then we can also get lava tubes. And this is where you have the surface of your lava flow has cooled, created this crust on top, but then all the lava inside the tube has exited and we get this void space. And a lot of places like in Hawaii, there are some lava tubes that are extinct that you can hike through. There's some that are still active that actually get lava coming through them on a regular basis. And then whenever those lavas end in water, ocean, lake, river, we end up with what are called pillow lavas. And we have some cool videos for you to watch showing those in this class. Lava domes is another feature that we see. So up at Mount St. Helens is a great example of a lava dome that has begun to rebuild that volcano after the 1980 eruption. These are typically explosive. So in this case here, we have some lava that is erupted, but that lava is so thick, so sticky, it doesn't flow very far from that vent, so we end up with this little ball of magma or lava just sitting on top. So these are technically lava flows here, but they're not flowing far from the vent. They're staying pretty close because they're so sticky. We get a lot of gases and a lot of ash that can be produced. Not nearly as much as the initial 1980 eruption, but each of these dome building regrowth cycles that the volcano goes through produces enough ash that might get the surrounding area, surrounding flanks of that volcano covered in a layer. Eruption column, so you heard me mention that term earlier. The eruption column is going to be this vertical part of the eruption. So depending on that height, we're going to break it into these different categories. So the eruption column is just that vertical nature of these eruptions, so that so much force of that material being ejected out of the ground, so much pressure built up inside that volcano can shoot your volcanic material up at various heights. Your eruption column can be tall, can be short, depending on how much pressure has built up. So these produce ash, gases, acid rain, and the distance it goes depends on how high that material has been ejected. If it's ejected high enough, it can get into these currents, these air currents that can travel all the way around the globe. Pyroclastic flows, these are explosive again. These are very, very hot, very, very fast, thick flows that rush down the sides of your volcano extremely fast and just incinerate anything in their paths. These end up leaving a pretty thick layer of debris that is just a jumbled up mess of material. There's ash, there's mud, there's volcanic rock, there could be trees. Anything that was in the path of this pyroclastic flow is going to be incorporated into that deposit. And if it's deposited hot, all that material can just be welded together to form a solid rock almost instantaneously. Then we have lahars. So this is where that hot volcanic material interacts with water or ice in the Cascades. We have glaciers on all of our volcanoes. So if there's an eruption, chances are pretty darn likely that we're going to have lahars. And here we can see in the bottom picture a lahar that came out during one of these dome building cycles from Mount St. Helens. So you can see the really dark stripes down that volcano, and that was a result of this dome building, melting the surrounding ice and snow, and then creating this mud flow that would just follow any of the river valleys downstream. Some of these are small, some can be huge. We're going to get into these in a little bit more detail when we start talking hazards. Lateral blasts, so in the case of Mount St. Helens, we had a lateral blast. This is where instead of your typical eruption straight up, Mount St. Helens actually blew sideways, so it created a lot more destruction than it would have happened if it went straight up. So these are explosive. We get lahars, pyroclastic flows, ash. This forms, these lateral blasts occur when you have the surface of your volcano weakened. And in the case of Mount St. Helens, it was weakened because you had that magma rising up inside the volcano, causing the surface to crack and deform, creating weaker parts of the volcano, and then we ended up having parts that just gave way in a landslide, which then provided a pathway for that lateral blast to move out of the volcano. So those landslides, so I mentioned Mount St. Helens, that can happen as a result of that deformation that happens on the surface of the volcano. But in some cases, like Hawaii, we have these lava flows that build out the coastline over time. But those lava flows, once they reach the ocean, start to break apart, and we get some material that gets all jumbled up. And what ends up happening is you get this top crust that's pretty strong, but the waves keep eroding away at the base, and we end up having areas that become weakened, they're oversteepened, and then we can get these landslides that can happen underneath the ocean surface and break off parts of the land. So there's actually a whole part of the Big Island right around in Volcanoes National Park that has actually slid slightly and could slide and break off into the ocean at any time. So to break down the difference between phreatic eruptions and magmatic eruptions, so the difference here basically is magmatic, we have magma erupting at the surface, whereas phreatic, we have steam and hot rocks interacting with hot rocks, and we end up with this more of a steam and ash eruption and less of the magma lava eruption. So with phreatic, there's really no new magma that's being produced here or lava that's erupted onto the surface, because we have that stuff pretty deep inside the earth, and the groundwater that filters down comes in contact with that, and then it shoots the steam and ash and any debris above that up and out. Whereas magmatic, we actually have that magma coming to the surface and getting these lava flows occurring. So we get much younger material erupted. So to talk about each of these, submarine eruptions, these can be a combination here of the two, of the phreatic and magmatic. So you can get just the ocean water interacting with the rocks and the magma and producing some what are called black smokers. So we get these usually around divergent boundaries, some hot spots like the Big Island. We've got a new volcano forming off the coast, the Lohi. So we end up with some of these features forming under there, but these don't actually breach the surface. They produce rocks that are basaltic in composition, but because they're cooling so fast from coming in contact with that cool water, we end up getting this pillow form that results in the rocks almost shattering. Once they're formed, they cool so fast that they shrink, they break apart and crack, and we get a lot of debris forming as a result. And when we have just the water interacting with that hot rock and then coming out at the surface, those end up producing what are called black smokers and spires on the ocean floor from that superheated mineral-rich water pumping out and then precipitating those minerals out. So here you can see a few examples. We've got pillow lavas here in the lower left. We've got one of these steam eruptions, hot water erupting on the ocean floor. And then here with these two examples, these are really, really close to the surface. So might be a little bit of land poking out in some cases here, but most of that eruption is happening underneath and it mixing with that water and producing these huge steam eruptions as a result. Subglacial, just like the name sounds, it's happening underneath a glacier. So we have, like in the case of Iceland, these are pretty common, where we have a volcano starting to form underneath the ice, and when that activity increases, it's going to melt the ice above, and you can see some depressions starting to form, and then because all that hot water melts the surrounding ice, we can get big outburst floods that can occur, releasing all of this water that formed and melted around that crater. We can also get ash and steam. So just a few years ago when I'm not going to bother trying to pronounce it, but there was a volcano that erupted and it caused some serious disruption with flights in Europe. So this can be a pretty big hazard. So when we talk about all of these different volcanic eruptions, we can actually categorize them on the Volcano Explosivity Index, so the VEI. So this is based on the size of the eruption, so how high did it go, how far did the material travel, and what type of material was ejected. So the ejecta volume and eruption column height are the most commonly used criteria for these. So we have a couple of different ways that these scales have been presented. Here you can see it goes from 0 to 8, and showing you the volume of material that has been erupted and then how high the eruption column was. And then showing you, it's a little small here, but you can see the various types of eruption styles that we just talked about: Hawaiian, Strombolian, Vulcanian, Plinian. So you can see there's some overlap with each of those. So in some cases there can be a little bit of gray area. It's not a perfect cookie cutter. This size is Hawaiian. There's a little bit of overlap there, and that's where looking at not only the size but what is ejected can help categorize those a little bit better. And here we can see some examples of recent eruptions. We're going to talk about a few of these in this class. If you're looking for a project topic, these could be the ones that we don't discuss later in the term, could be good ones to choose. So to look at some that we're familiar with, so teeny tiny one over here, very, very small, Lassen Peak, and then Mount St. Helens here in green. You can see, like I said earlier, relatively small in the scheme of things. When we look here at the Yellowstone eruptions and the Toba eruption that occurred, you can see just how much larger those eruptions were. So if you thought Mount St. Helens was big, there have been larger ones too. So that about wraps it up. We've gone over all the different types of eruption styles, why they're different, and how we categorize different eruptions. Make sure you check out the reading material and video links I have. You can see examples of most of these eruptions posted there.